Okay. If we find representations like that, and programming is such a rich field for doing so, if we find representations like that, a number of things would follow in our mathematics education world. First of all, we'd increase reach. There would be people who are hitherto barred from participating in this amazing world of mathematics because they don't understand the representation system. They don't understand the infrastructure on which it's built. We can make new connections, which I've already said. And lastly, we can rethink knowledge structures. So what we think an object, a mathematical object is about will change, as I said, depending on the technology we have available for its expression. Including, for example, the order in which we teach. We take for granted that we know for sure that there's a certain kind of natural ordering. You learn about linear equations before quadratic equations. Well, that's not a bad idea, and it's an essential idea if the only technology you have at your disposal is pencil and paper. But if you have dynamic technologies at your disposal, maybe it makes sense to start with a more interesting equation, and then asking, what about the special case when the order of x is only 1? You can imagine that kind of thing. Well, here's another example that I love. We always teach about constant velocity before we teach about acceleration. Right? It just feels that must be a natural ordering of the topic. Why? Well, acceleration is a second-order differential equation, and it's quite tricky, and it's much more complicated. And little force diagrams of acceleration feel much worse than the trouble is, of course, that nobody in the history of the planet has or ever will experience what constant velocity feels like. So in terms of looking for bits of mathematical approach with technology that do this job of helping you identify with the mathematical object, it's a non-starter. It's exactly the wrong thing to do. Because we've all had the experience of being in a car at constant velocity and it doesn't feel like it's moving much, except the only times that it does feel like it's moving is when it's accelerating, obviously. But going around the corner is a different kettle of fish. And of course, that's a very, very hard idea. 99% of every person I've ever tried to teach this to says, yes, but when you go around the corner, you're not getting faster, so you can't be accelerating. If you can feel what it means to accelerate, that particular way of thinking can be challenged. And it's a nice picture, don't you think? We haven't succeeded in doing this so far. Despite 30 or 40 years, we haven't really made the progress that we think we should have made. Papert wrote a wonderful one-paragraph, what do you call the things that go on the back of books? No, not an acknowledgement.
Review, blurb.
Blurb. There isn't a technical word, surely. This is the most amazing book, I think, mathematics book that I've ever read. It starts on page 1 with the definition of a square in logo, and it finishes at the end of chapter 8 with a model of general relativity. And I love that. I love it. I especially love it when people come and say, oh, logo, squares and triangles and circles, we did that when I was at school, I'm not interested. I say, yeah, that's fine, come back when you've read chapter 8. But Papert wrote on the back of this book, this is the first of a generation of textbooks of the new type. And it was the first in a generation, but it wasn't followed up by thousands of other examples. There are some wonderful examples in the book by Al Cuoco about algebra, and it's computerized algebra, not in the sense that Maple and mathematics are, but you write computer programs to simulate the algebra that you're trying to express. And this is a little book. I'm not advertising at all because it's long out of print. But it's a book with some substantial number of thoughtful contributions about the role of programming for learning mathematics, but it hasn't been followed by thousands of examples, which you might expect if life was simple. I'm going to just do one more slide. This is Seymour speaking just before his terrible accident in Vietnam, a few weeks before, I think it was. And he launched what has now become known in the circles that Celia and I move in as Seymour's 10%. And I'm going to stop when I told you what that is. Seymour's argument is very simple. We have huge amounts of energy and money spent by governments and funding agencies to teach better what we already teach. Kids have difficulty with this area of mathematics. Let's put money into solving the problem. Let's fund a research project to help kids. Let's write computer software to help them understand it. Let's do everything we can. But we don't acknowledge enough that the subject matter itself, what he calls the what of mathematics rather than the how of mathematics, we don't acknowledge enough that the curriculum as it's been passed down to us, primary school, secondary school, universities particularly, is pretty arbitrary actually. I mean, naturally there's only a point something percent decreasing exponentially every second. There's only so much mathematics that you could teach people. But what we actually do teach is not in any sense canonical. It's not natural. It's not completely arbitrary. But what Seymour says is, look, it's fine to care about the how of teaching. Let's spend 90% of our time studying the how of teaching and learning. But let's try and reserve just 10% of our time for thinking about what it is we're trying to teach.